building. Great, so welcome back everyone to the last session of today, and we have Kate Scholberg joining us from Duke University, who will be talking to us about coherent neutrino scattering. So thank you very much, Kate, for being here, and whenever you're ready, please go ahead.
Okay, thanks. Thanks for having me, and I'm going to give you an overview about coherent elastic neutrino nucleus scattering, mostly on the experimental side. So here is an outline of what I'm going to talk about. I'm going to tell you, probably already heard quite a bit about neutrinos and neutrino interactions, so that will be super brief. I'll tell you about coherent elastic neutrino nucleus scattering, some physics motivations for measuring it, how we go about measuring it, and the experiment that I work on, Coherent, which has made the first measurements. So I'll tell you about that. And then I'm going to broaden it and talk a little bit about other SEVNS experiments worldwide. Okay, so I think you've heard in the last, at least in the last talk, and a few more about neutrino interactions, and you've probably heard about the high energy end. If you have very high energy neutrinos, you're actually scattering off quarks inside inside a nucleus, inside a nucleon, and that will often, at these energies, you will often have enough energy transmitted to the nucleus that you will blow up the nucleus. It will be quite a lot of debris. Going down a little bit in energy, this is the regime of importance for long baseline experiments you've heard about. So long baseline oscillation experiments where you have GeV energies and you have interactions with nucleons inside the nucleus. These can also be disruptive. You can make hadrons and so on. There's lots of stuff going on there. It can be quite complicated. Going down a little more in energy, this is actually the regime for solar and supernova neutrinos. You can have interactions with nuclei and electrons, and these, when you have an interaction with a nucleus, this tends to be less disruptive of a nucleus, but you can still have some kind of debris. But what I'm actually going to be talking about is the very lowest energy regime where you have very low momentum transfer to the nucleus. It's just a gentle scatter of a neutrino with the nucleus. This is really the gentlest of the neutrino interactions. It's just a kick of a nucleus and the nucleus rolls off. So this is the coherent elastic neutrino nucleus scattering regime, and it's a neutral current interaction, exchange of a Z boson, and the nucleus recoils as a whole. To make that criterion for coherence a little bit more quantitative, it's when you have the momentum transfer Q times the size of the nucleus small. This is the quantitative condition for coherence. And the result of this is that it's a generally coherent condition where you have the total cross-section, which scales as the cross-section off a single constituent times the square of the number of constituents. And basically, you can think of that as all of the nucleon wave functions in the target nucleus in phase with each other, so that to the neutrino, the nucleus just looks like a single blob, like a single point without substructure. And this kind of interaction was actually first proposed a long time ago in the 1970s by Dan Friedman. And he wrote a paper where the abstract is here and the beginning of the paper is here. He called his suggestion for the existence of this interaction, he called it an active hubris because of the grave experimental difficulties for actually observing it. Now, before I go on, I'm going to make a little comment here. I'm not talking about this process. You probably heard in some previous talks about this kind of process. This is also a coherent process. This is coherent pion production. This is an inelastic process. This is where you have a creation of a pion in conjunction with the interaction, but it is not elastic. And so this is not what I'm talking about. This is a much higher energy process. Okay, so I'm going to do a poll here. And the poll is here. How do you pronounce this acronym, CEVNS, that I'm using to describe this process? And so let me see if I can figure out again how to do the slides. Now I have lost the settings here. View poll. So get rid of this poll. Okay, sorry, I just did this just now, and now I can't find the share. Okay, it's share contact and polling. I'm going to do a multiple choice poll in the poll. Okay, so I've got A, B, C, D, E. Oh, I can only have, oh, I'm only allowed 5 choices. So you'll have to ignore the last one. But let me start this poll. How do you think it's pronounced? Is it poll? I can't move the poll, so I can't see what my choices are. But we'll see. Is it Ken's, Kent's, Kevin's, Sens, Sevens, Sets? Okay, we got a bunch of responses. I'm going to do show responses. Okay. Of course, you can always pronounce it however you like, but okay, so let me end that. Okay, so the answer, at least the one that I prefer, is sevens, and that is the one that I think a lot of people are using. So it's maybe a silly pronunciation, but well, I think it works. Okay, and so here, just a note on that, some of the reason for using that nomenclature is that I think it's important to include elastic. Some people have used in the past CNS, but that confuses it with coherent pion production. CNNS, I've been told by nuclear physicists that to them that means nucleon, nucleon. I'm okay if you want to put a Greek letter nu in there, but it's always annoying to change the font. So anyway, I'm asking you all to spread the meme of using the pronunciation sevens. Okay, so that is a side note. Okay, so here is the standard model prediction for the differential cross-section for sevens. And this is basically the probability, if you have an interaction, that you are going to kick the nucleus with recoil energy T. And the normalization gives you the absolute probability for doing that. And so let's look at inside this expression here, and this GF here is the Fermi constant. This is a standard model parameter that really tells you what the scale of this interaction is. It's a weak standard model interaction. This part here is the kinematics. So this is really telling you that it's an interaction. It's kind of like, it's like a ping pong ball hitting a bowling ball, and this tells you what the maximum energy recoil of the nucleus is. That's when this is 0 is where you get the maximum. And it's really actually very much like a ping pong ball hitting a bowling ball. It's actually hard to get that bowling ball rolling too fast. This quantity here is called the form factor. This is where the information about the distribution, the space distribution of the nucleons in the nucleus is. It's basically the Fourier transform of the space distribution. If this factor is 1, if it's exactly 1, then it's a fully coherent interaction. There's no substructure, and the nucleus looks like a point, just a structureless object. But that's not exactly true in real life. There is some structure. And this quantity here is the weak nuclear charge, which can also be written like this, where N is the number of neutrons in a nucleus. Oops. N is the number of neutrons in a nucleus. This is the coefficient. Z is the number of protons in a nucleus. This coefficient here, if sine squared theta W that's another standard model parameter, that's about 1/4. If you multiply that by 4, you get about 1. 1 minus 1 is about 0. And so this coefficient is small, which tells you that this weak charge is approximately proportional to the number of neutrons. It doesn't really care very much about the number of protons in the nucleus. The neutrino is not really seeing the protons, it's seeing mostly the neutrons. And so what that means is that so there, I just moved that up to the top, that this cross-section is proportional to the square of the number of neutrons in the nucleus. And so here, this is a flux average cross-section. This is averaged over a flux that will be important later. This is just showing the n-squared dependence, and these particular nuclei here, these are the n values for those nuclei, are plotted here. This black thin line is if there were no substructure at all, so if the form factor is 1. The green line is using a particular form factor, and this width of that green line is the uncertainty on that. And so this is showing you there is some suppression from substructure, but it is well understood. Okay, and this cross-section is very large by neutrino standards. Neutrinos, of course, are famously weakly interacting, but by this cross-section, by this interaction, it's relatively large, and that's thanks to the coherent enhancement of the cross-section going as the square of the constituents. And this is just an example here. So this blue is the 7's cross-section for 2 reasonably large nuclei, cesium and iodine, which I'll show you. There's a reason for those being chosen. This green is an example. This is an actual measured cross-section, not measured very well, but it's a measured cross-section. This is a charged current interaction on iodine. And you can see that there's a couple orders of magnitude difference. And so this green one is kind of a standard interaction, neutrino interaction of the kind that you've been thinking about. And it's really a quite large enhancement from the coherence. This red is inverse beta decay on free protons. That's also a well-understood, well-known interaction, also relatively large per mass. And even that is smaller. This dashed red line is interaction on electrons. This is per target atom in cesium iodide. That's much smaller. So this is really a very large cross-section by the standards of neutrinos. But you might think, well, what's the deal? Why was Dan Friedman talking about how gravely difficult it is to measure this? And the reason for that is the kinematics. It's the ping pong ball hitting the bowling ball. It's easy to do, but it's hard to make that bowling ball get rolling very fast. And this is an example. This is the shape of the recoil spectrum that you get. This is for germanium, which is kind of a medium-sized nucleus for 30 MeV neutrino. And what you see here is that the maximum recoil energy, it goes as E squared over M, and it works out to 25 keV for germanium for a 30 MeV neutrino. And so that is very, very tiny. That is very hard to measure if you compare to, for example,
It seems Kate is having some connection problems. Let's see if it resolves by itself in a minute or so. Apologies to everyone.
Hi, are you there?
Hi.
Yes.
You
Hi,
could
I'm sorry.
reconnect.
I completely lost my network connection. In fact, it's still not working. I haven't had any problems at all here, but it just completely cut. I'm using my phone hotspot now, actually.
Don't
So
worry. At this point of the pandemic, we are all used to this.
No
yes,
problem at
sorry
all.
about.
Welcome back.
So I will turn my video off because it's probably bad bandwidth. But
That's a good idea. Yes.
yeah, okay, yeah. Sorry about that. I hope it it holds
No
for a
worries.
while. Okay, all right, yeah. So I guess I was here. I was talking about the very tiny coil energies, which are, uh, compared to, for example, Super K would have about an MeV threshold, and it's very tiny compared to that. Okay, so oops, how do we measure this? Well, the only signature is you have to somehow gather that tiny energy that's deposited by a nuclear recoil in the target material. And we have actually benefited in the past decades from having a lot of detector development exactly for this goal of actually looking not for neutrinos necessarily, but for WIMP dark matter, which creates a recoil which is exactly the same kind of recoil as as you would get from a neutrino. And so we actually now have a lot of detector technology which is sensitive in this range. Okay, so now let me talk about why we care. Why is it interesting to look for sevens? And there's a long list. I could do several talks on this, but I will just make some highlights. So first of all, sevens, it's a signal for signatures of new physics. And the idea here is that it's really a very cleanly predicted cross-section in the standard model. So unlike at high energies where you have lots of nuclear effects, you have final state interactions, you have all kinds of messy stuff happening in the nucleus after the interaction, that's not the case for sevens because you have a very simple interaction of an entire nucleus. Here's another way of writing the cross-section where I've written it out in terms of the standard model couplings. And so the vector coupling here is dominant. There's also an axial vector coupling if there are unpaired spins in the nucleus, but this is actually quite small for most nuclei because there are fewer unpaired spins than there are nucleons. For a spin zero nucleus, this is actually pretty much exactly zero, this one here. It's pretty cleanly understood. There's this form factor, which does quantify some substructure in the nucleus, some finite size of the nucleus. And the bigger the nucleus, the stronger this effect is. And so this is an example of the form factor as a function of momentum transfer. For bigger, fatter nuclei, it's a bigger suppression. Also at higher momentum transfer, it's larger. But this is a fairly well understood, it's just a shape effect. There are really quite small uncertainties on this. And just to see that, this is the flux average cross-section, and this green width of that line represents the approximate uncertainty on the form factor for as a function of n. And so the idea here is because this is a well understood cross-section, the signature of some kind of beyond the standard model physics would violate this n squared dependence. And so what you want to look for is a difference from expectation. And this is an example. This is a common parametrization for some kind of new physics that could be manifest in interactions of neutrinos with quarks. These are so-called non-standard interactions, and you can parameterize it by writing a Lagrangian with just throw in the extra interactions, and epsilon gives you a measure of the size of that interaction. If you have epsilon of 1, that's approximately standard model scale. You can have flavor changing interactions or non-universal one. The non-universal ones are just the not flavor changing, so it's lepton non-universality. And some of these are quite poorly constrained. And just to give an example of how that would manifest itself in sevens, what you'd get is, if it's a heavy mediator that's creating the new interaction, you would have an excess or a deficit with respect to the standard model expectation. This is just a parameter space. On the y-axis, it's a new interaction of electron neutrinos with up quarks. On the x-axis, a new interaction of electron neutrinos with down quarks. And what you would get is, if you can have positive or negative values, and they could conspire to have give you exactly the standard model rate, in which case you have no sensitivity, and that would be those sort of pale lines here along where these diagonals where it says you match the standard model rate. You could have a suppression with respect to the standard model rate if the parameters fall inside in this blue area, or if they're on the wings, you would have an excess. And so if you see something different from the standard model rate, you can constrain elsewhere. This is assuming all the other parameters are 0. It's a simplified situation, but it gives you the idea. Here's another example. You can actually look, this is another example of physics beyond the standard model. You could look for sterile neutrino oscillations. Sevens doesn't care about the flavor, and so if you have a sterile neutrino oscillation, a disappearance, it's a kind of a true disappearance. You get some spectral information in the recoil spectrum. If you have multiple detectors, you can cancel systematics, and this is just an example of the kind of sensitivity you would have. Typically, this is quite hard. You need large statistics for a disappearance experiment, but it's conceivable that you can go after this kind of physics with sevens. Just another example of what you can probe with sevens is a neutrino magnetic moment, anomalous one. There is a very small standard model neutrino moment and magnetic moment that's expected, but that's very, 8 or 9 orders of magnitude below the current limits. You could have an anomalous one, which would manifest itself as a distortion in the recoil spectrum at low recoil energy. And this is just an example of the kind of signature. This has been explored in the literature as well. And another one is this is actually kind of another different way of looking at non-standard interactions. If you the weak mixing angle is embedded in this weak charge here, and so if you measure the rate, you can measure the weak mixing angle. If you see something different from the expectations, that can be an indication of new physics. And so you can cast the search for non-standard interactions as in the form of a measurement of the weak mixing angle, which is maybe a different way of looking at it. Okay, now sevens as a signal for understanding of old physics is old but still good physics of nuclear physics, and we can actually learn about the form factor if you have a precise enough measurement. The uncertainties on this form factor currently are quite small, at the less than 5% level, but if you have a precise enough measurement of the recoil spectrum, you can actually observe by looking at the recoil spectrum shape, you can actually determine the, you can actually map out the form factor. So this is something that you can do, and this is just showing you it is very small uncertainty. This is the example for cesium iodide. This is the recoil energy spectrum. On the right-hand side is the just changing variables to the momentum transfer spectrum, and the width here you can see is the uncertainty of the form factor from it. So you can see it's very small at the current level experimental precision, but it's something where it's a new way of measuring it, and we can hope to get to the precision of measuring it. You could ask the question, and some have, is suppose you're hunting for new physics in the distortion of the recoil spectrum. Well, it's kind of annoying that if you have uncertainties in the form factor that can increase the uncertainties for looking for that new physics. And there are certainly degeneracies in the observables between this old physics. If you see a distortion in the spectrum, that could be just think of that as a measurement of the form factor, or could it be something new and exciting? And so we do have to think carefully about how to disentangle these effects in the long term. When we get to the point of the precision of the in the measurements, as that approaches the precision of the form factor knowledge, then we are going to have to start working about thinking harder about this. At the moment, the measurement precision is much worse than the form factor theoretical uncertainty. So here's what we can get at experimentally if we're going after new physics. The observables are really the event rate, the recoil spectrum. In principle, you can measure also the scattering angle. That's experimentally currently pretty hard, but something we could maybe go after in the long term. I have to mention here that there are systematics in the spectral shape, but it's something that we are continually improving. There are knowable parameters here. You can know what the flavor is via the source, which I'll say more about. You know what your nuclear target is, so you know N and Z, you know the baseline, and you know the direction with respect to the source. So these are the observables you have to work with. Okay, so now let me talk about sevens as a background for signatures of new physics. And here the new physics I'm talking about is dark matter physics. And so, in fact, sevens from natural neutrinos creates an ultimate background for direct dark matter search experiments. And of course, this search for direct WIMP detection has really aided sevens measurements by improving the technology, but they are linked as signal and background. There's what is called the neutrino floor, and actually this is kind of also a signal opportunity. And the idea here, so this is the kind of plot you make if you do direct dark matter. This is the cross section of WIMP matter interaction. This is the mass of the WIMP. And what experiments do is look for a signal in this parameter space or exclude regions above this some particular limit line. This dashed red line is what's called the neutrino floor. These are the WIMP parameters at which the signal from natural neutrinos, such as solar neutrinos or relic supernova neutrinos or atmospheric neutrinos, is actually creating recoils in the detector that fake the WIMP signal, that give you a recoil spectrum that is indistinguishable from the expectation from WIMPs. And that, so basically if you're at this parameter, neutrinos from the sun are going to blind you for WIMP detections. And so that's what's called the neutrino floor, and that is limiting eventually the sensitivity of dark matter experiments. But it's actually also an opportunity for a signal, and I'll come back to that in a bit. I mean, this is actually WIMP dark matter detectors can see neutrinos via sevens. One thing I'll mention also, this is another instance of sevens being a background is for accelerator-produced dark matter. In fact, this is something we've been spending a lot of time on recently. And I won't say too much about it, but there's more coming out soon, where the idea is you can create dark matter in a neutrino source that you're using for sevens measurements, and that dark matter there's different models. You can have a so-called vector portal, mixing of a vector mediator when in photons from decays in the source, and then what you end up with is a particle that creates a recoil that looks just like sevens. And so this is another interesting thing. This is maybe a bit of a diversion, and I won't come back to it, but you will see more about this in the literature later. Now getting back to sevens as a signal for astrophysics, it's a background for dark matter, but it could be a signal for neutrino physics. Here's on the bottom is a plot of natural neutrino fluxes. These are the ones that make up, the ones on the bottom are the ones that make up the neutrino for solar neutrinos. There's the DSNB, that's diffuse supernova neutrino background. That's neutrinos from all the supernovae that have occurred over the history of the universe, making their way to Earth. And then there are atmospheric neutrinos. This pink is the supernova flux during the 10-second burst. That's a burst flux, so that's a transient kind of signal, but it's in that energy range. Now, if you superimpose on here, this is the maximum recoil energy you get for an argon target, and these are thresholds here. Horizontal lines would represent a threshold here. Conventional WIMP detectors are, you could see here, therefore sensitive to pretty much all of the fluxes greater than 10 MeV or so. If you want to be sensitive lower than that, you need a much lower threshold kind of detector. So, you know, it's really, most WIMP dark matter detectors will be sensitive to these signals. And an example of that, of this being a signal in a WIMP detector, this is a recent paper from Search for Sevens from Solar Neutrino from the Xenon 1-ton experiment, which is a xenon-based dark matter experiment at Gran Sasso. And they have a limit. They haven't been able to actually see yet observe a signal from the solar neutrinos, but eventually they're going to get there. They actually have you can convert their measurement into a limit on the Sevens cross section from solar neutrinos. And so they haven't seen it yet, and the other dark matter detectors haven't seen it yet, but eventually it's going to hit the floor, and I just have to point out that that really is an interesting place to look. Let me make a couple of mentions of neutrinos from core collapse supernovae. This is one of my favorite things. These are events where you have enormous fluxes in a very short period of time of neutrinos of all flavors. Basically, the time scale is prompt. It's tens of seconds, maybe most of them in a few seconds. And it's equally distributed approximately between flavors. Okay, so here's another poll. Now I have to figure out how to do the poll again. I've actually lost my, and so here, what these are counts over threshold as a function of recoil energy. So it's an integral spectrum. And what I'm hiding with this, this box is a poll. And what I want you to do is to tell me which color line corresponds to which nuclear target. You can see there's kinematics happening here. One of these targets has more interactions, but they are at lower recoil energy. Another of these targets has more interactions at higher recoil energy. And so what I want you to guess is what is the ordering of these. Let's see if I can figure out how to do this poll again. What would be share content, polling, multiple choice. And so I've got 4 choices here. Okay. Oops. It seems we should do polls with fewer choices, otherwise it takes time. All right. Okay, so I'm starting the poll. Go ahead and let me know what you think the answer is here. Well, it seems pretty uniform. Wait a few more, a little bit longer. These polls, it's like microwave popcorn. So you have to wait until the rate of responses go down. Okay, I'm going to show the responses. Okay, it's pretty uniform distribution. Okay, so the answer here is that the red is argon. So that's the lightest nucleus. And so you're going to get more of them kicked to high energy. The blue is xenon. That's heavier. And so you get fewer of them kicked to high energy. So that's it's basically just kinematics. It's just imagine hitting a smaller versus a bigger bowling ball, more or less. Okay. Okay, another question. Okay, another poll is, why is this an interesting signal? So why would you want to measure sevens from a supernova in a ton scale dark matter detector? Is it because it would dominate the worldwide supernova signal? Is it because it's sensitive to all flavors of the burst, or is it because there's good energy resolution? So let me do this again. Make another poll. Oops, only 3 this time. Okay. All right. What do you think? Which is the best answer of these 3? Okay, I'm going to show the response. Okay, I think the winner is the right answer. So the right answer is it's really, so it won't dominate the worldwide signal. There's basically about a handful of 7 events per ton. You can actually see, read on here, per ton, it's only going to be, you know, maybe a dozen if you have a really low threshold for a 10 kiloparsec supernova, which is the center of the galaxy. If you compare to Super K is going to have thousands of events, so it's not going to be dominant unless, you know, if you had kiloton detectors, it might be dominant, but it's not dominant. It's also not great energy resolution because it's a recoil spectrum, so you can't really tell event by event what the energy is. It's some, but it's not going to be the greatest. So really the best answer here is it's because it's sensitive to all the flavors of the burst, so you can tell. You can actually measure the entire neutrino content of a supernova burst from looking at the 7 events, and so that's really the advantage. That's the best, most exciting reason to measure supernova neutrinos with dark matter detectors. And here's an example. This is in xenon here. This is an example of the events. This is in Darwin, which is a next generation xenon experiment. And so these, this is great as a function of time for a particular model where you would, you know, it would be hundreds of events. It'd be pretty good, but it's still not as many as Super K. So, but really, this is exciting because you get the entire flavor content of the burst. And so it's like this neutrino floor is somehow coming up and smacking you in the face for about 10 seconds. It's really would be a really great great observation. Okay, so now let me talk about the experimental aspects of how you actually go and measure 7s. As I think I showed this slide before, it's really looking for some very tiny little whisper of energy. You have to somehow couple that into something that you can measure and digitize and analyze. And there are many detection strategies. In fact, this is a slide that I stole from a dark matter talk. Many of the same strategies for dark matter detectors also work for 7s. And so you can look for light. So the energy can couple into photons. So you see a little flash, and there's many examples of that. Noble liquids are scintillators. You have special scintillating crystals. You can gather ionization, and that is the strategy for example, germanium, where you get a you have a high voltage and you gather charge. You can also have phonons or heat, bolometer kind of detectors where you're measuring the total energy deposition in a material. And you can actually use more than one strategy at a time. There are different examples of multiple detection channels, and actually looking at relative amounts of energy in different channels can help you select recoils from background. And so this is very much aligned with dark matter detection. And what kind of thresholds do you need? So this is I showed this before, this is the maximum recoil energy, goes as E squared of m as a function of neutrino energy. And these are a kind of different neutrino spectra from different kinds of sources, and I will talk in more detail about some of these. So the blue is from a stopped pion source, the green is from a nuclear reactor, and the orange is from a radioactive source, an artificial radioactive source. And so if you compare that to the maximum energy you get, what this tells you is that if you want to be sensitive to stopped pion neutrinos, a conventional WIMP detector, which has a threshold of maybe several keV, so where this black line is, this is going to be good enough, but it's hard to get reactor neutrinos. If you want to see reactor neutrinos, you really need to have thresholds of below a keV, and that is very challenging. You need really special detectors and low background detectors too. If you want to see something like, for example, source neutrinos, you need really very low thresholds. So this is the energy threshold is a very challenging issue. Also, the cross-section increases with energy. And so this is an example here. On the left, this is the same plot, just E squared over M for an argon target. On the right, what I've done here is I plotted the number of events you get. So basically the observed recoil spectrum for monochromatic sources. And so the green is for a monochromatic 3 MeV neutrino source, which is typical from a reactor. The red is for the same flux. It's for a monochromatic 30 MeV neutrino source. And what you see here is not only does the red have a higher recoil energy, which I just talked about on the previous slide, but it also has more events because the cross-section is higher. It goes as the square of the neutrino energy. And so you want the energy really to be as large as possible. And so you might ask, well, why not higher energy even? Well, you can't go too high because eventually you will start to no longer satisfy the coherence condition for which is that Q has got to be less than 1 over the size of the nucleus, and this energy is about 50 MeV for a medium-sized nucleus. Because eventually what happens is if your energy of your neutrino is high enough, you will preferentially scatter off nucleons instead of nuclei, and you will no longer have a high fraction of coherent interactions. You're going to have regular charge current interactions, eventually even deep inelastic scatters. So it's really, you want to stay below about 50 MeV if you want a reasonable fraction of seventh events. And so the kind of sweet spot here, which is really a great way of measuring sevenths, is to use neutrinos from pion decay at rest. This is what you get when you throw protons at a target. If you create pions, then you let the pions, if you stop the pions in a dense material and let them decay at rest, you get a spectrum that looks like the upper right here. And so you get here a two-body decay, and this is really very nice. You get, it's a two-body decay, and so your final state energy is well known. It's a monochromatic 30 MeV muon neutrino. This is prompt. And then when the muon decays at rest, you get a three-body decay spectrum. So it's a range of energies up to half the muon mass on the muon decay timescale. And this is a well-understood spectrum. These spectra are known very well from understanding of weak interactions. So this is really a beautiful kind of neutrino source. It's actually the kind of source that has been used before for neutrino physics, for LS&D, for example, and at ISIS. And so here's a figure of merit plot for different kinds of pion decay at rest sources, where this axis here is the power, which is approximately proportional to the neutrino flux. It's the power of the protons. And you want this to be large. You want lots of neutrinos. The y-axis is the reciprocal of the duty cycle. This is basically a measure of how tightly pulsed the beam is, because if the beam is very pulsed in short pulses, that is very beneficial because you know when your neutrinos are coming, and you can also characterize your background by the off-beam counts, and so it's really very helpful. And so you want this to be large, and so you want to be in this upper right-hand corner. And what I'm going to talk about is the measurements of the spallation neutron source, which is in Oak Ridge, which has really very good properties. This one here, FTS plus STS, there's actually a planned upgrade, which will increase the available neutrino flux. So let me say a little bit more about the spallation neutron source. This is in Oak Ridge, Tennessee. The proton beam energy is around a GeV. The power is actually now regularly 1.4 megawatts. It's actually going to be upgraded over the next several years to 2. The pulse duration is about 400 nanoseconds, so it's very sharp, much shorter than the muon decay timescale. and it occurs at 60 hertz. And it's got this huge mercury target, which is enormous and dense, and basically every pion that is created immediately stops and decays at rest. And the neutrinos are free. It's really a byproduct. The whole facility was built for other stuff, to make neutrons for material science and stuff like that. And it's really just really great luck that it produces neutrinos, beautiful neutrinos as well. So this is the time structure. There's a prompt muon neutrino from pion decay that is in time with the proton pulse. So those are prompt. Those are new mu's, very pure new mu's. Then there are anti-new mu's and new e's on a muon decay timescale that come from the muon decay at rest. And this, when it happens at 60 hertz, the background rejection factor is a few times 10 to the -4. So it's really a very, very good source for that. It's also very clean in the sense that almost every neutrino comes from a pion that decayed at rest, and this is a log scale. So this is the same plot that I showed you a couple of slides ago. It's the same shape as oops, I guess it was more than a couple of slides ago. It was the same shape as this one, except that that's now on a log scale and squished. Go back here. And this stuff comes from a detailed simulation, and it is down by several orders of magnitude. It's this kind of grass out here is much lower, much lower. Okay, and so the collaboration that has taken advantage of this is called Coherent, and so this is the Coherent collaboration. It's about 90 members. We've got 4 countries and 20 institutions. And we have 4 detector technologies, and I'll tell you in a bit more detail about some of them. We've got cesium iodide crystal that's now completed, and that was the first measurement, and that was deployed about 20 meters away. This is a scintillator. It produces light from recoil energies. We have liquid argon. That's also a scintillator. It's a single-phase liquid argon. We are deploying germanium right now. That's not a scintillator. And we are also deploying sodium iodide. And so we have these four technologies. And we also had very good luck in finding a great place to site these detectors. We have what's called Neutrino Alley. And this is a corridor that runs parallel to the proton beam. So this is where the SNS is. There's a proton beam that hits the mercury target, which is right here. And the neutrinos come out isotropically from that target. So we can just sit in the glow of the neutrinos. This is a basement corridor. It's got actually about 8 meters water equivalent of overburden, which is nice because we have a little bit of cosmic ray protection. And we can put our detectors along this hallway here. And the cesium iodide detector was the first one to get data, was placed about 20 meters away. The argon detector I'll talk about is in the corner over here. The germanium and sodium iodide detectors are going in between here. So this is the expected recoil spectrum. So this again, it's the bowling ball hitting or the ping pong ball hitting the bowling ball. These are the different spectra that you expect. This red is the cesium iodide. That's the heaviest one. You get less kicked to high energy compared to, for example, the sodium, where you get more high energy. This is scaled by mass and distance from the target where we're going to deploy them. And okay, so here's another poll. How many counts are expected in 10 kilograms of argon? Okay, if 100 counts are expected in 10 kilograms of argon at 20 meters, how many are expected in 100 kilograms at 40 meters? Okay, so this is just a simple scaling question. So let me do that one. 5. Takes a little while to make these choices here. Okay, go for it. What do you think? one takes a calculation or two. I think I have two D's there. Plus one is actually E. Okay, I'm going to show the responses. People are still checking in here. Okay. Okay, well, the D's win. So this is just scaling. If you've got 10 times the mass, you would have 10 times the counts. And if you are at twice the distance, you get a quarter of the counts. And so the answer, the best answer here is 250. Okay, and so that's exactly how I have scaled those plots here. It's just inverse square and linear with mass. Okay, let me comment on backgrounds, which is actually most of one's life as an experimentalist, is you're always fighting backgrounds. And in this case, you get the usual suspects. You get cosmogenics, you get ambient and intrinsic radioactivity. Every detector has its own insanities. There's often detector-specific noise and dark rate and other things. Neutrons are especially scary in that it's a neutron source, and neutrons can bump into nuclei and make little, make signals that look just like either WIMPs or sevens scatters. And the problem with something like the spallation neutron source is that unlike steady state backgrounds, which can be measured off beam pulse, if you have an in-time background, you have to measure it and characterize it very carefully. So we have to spend a lot of effort to try to understand the neutrons in the background, which are in time with the beam. And in fact, there's one kind of interesting kind of in-time background. This is neutrino-induced neutrons, which we call NINs. And here the idea is that you can actually have charged or neutral current interactions of neutrinos with, for example, lead shielding. And lead, in fact, is particularly bad. It doesn't hold onto neutrons very well. What happens is if you have a charge current interaction, for example, with lead, can create a final state nucleus that spits out a neutron, which can then float into the detector and make a recoil. And the cross-section for this, although it's smaller than sevens, it's actually not that small. And this is an example on the bottom right here, is the blue is the germanium sevens cross-section. The black is the NIN cross-section. And, it's not that small. It's not huge, but it's enough that we have to worry about it. And so we have to carefully design shielding, and we have to make sure we take this into account. And it's actually an interesting signal in itself. Okay, let me talk about the first detector, the cesium detector. This was built and characterized at the University of Chicago. These are two students who got the first PhDs on this, no longer students. And this is a small detector. It was a handheld detector, which is unusual for neutrinos. This is with the shielding in Neutrino Alley. There's various layers of shielding, starting from water down to low background lead and poly. The first light measurement is shown here. So the measurement was of the recoil spectrum and the time, and both of these are usable to distinguish from background, since we can predict the background exactly. So here's the spectrum in charge, which is proportional to recoil energy. It's the photoelectrons from photons, which come from the recoils, and this is the time as well. And this is just the projection here, background subtracted projection of the the energy spectrum, so integrated over time. You can see the contributions from the different neutrino flavors, and this is there's a little tiny skin, you can barely see this, of the prompt neutrons. So we have actually very small prompt neutron background. And even that measurement, this was the first measurement, was a 30% measurement. Even that was enough to set some constraints on the neutrino non-standard interactions. And this is an example of that parameter space I showed you. The gray is the previous constraints from neutrino experiments, and what we were able to do is constrain in that blue area just from that first measurement. And there's actually been a lot of other explorations in the literature of the power of this measurement to constrain non-standard interactions. So we have one down after this, and we want to map out the n-squared dependence. And so we're going on to the next detector. The next detector to make the measurement was liquid argon, and this was in the corner neutrino alley. And this is a single-phase liquid argon detector. It's basically a bucket of liquid argon that is viewed by two photomultiplier tubes. There's wavelength shifter in there to shift the light to the good range for detection by the photomultiplier tubes. Also layers of shielding. And this is in the corner. Unfortunately, there's more neutrons in the corner, but it's still tractable. In scintillation from argon, you can use what's called pulse shape discrimination. There's basically different waveform shapes. The waveforms from nuclear recoils are shorter and sharper than the waveforms from, say, electrons and gammas. And so this is actually a very common technique for dark matter detectors. What this plot shows is, this is from calibration data. It's the fraction of light in the first 90 nanoseconds of the pulse. There's an example pulse versus energy. And for neutrons, this F90 tends to be larger, so it's a shorter, sharper pulse compared to a longer trailing electron signal. And we can actually select the recoils quite nicely. And so we do that. We do have more beam neutron background. There's actually some channels in the ground where the neutrons are coming and end up in this corner. This is where the cesium iodide was, which is much quieter, and it's really but it's still a reasonable situation where we can fit and remove that background. And this is the result plot. And so we use actually three things to fit. There's the time distribution, the recoil energy. Those are the same things that were used for the cesium iodide, but we also use this pulse shape discrimination parameter. And what you can see is the best fit is the green with the error bars on it here. And so this is the time on the left. The upper right is the recoil energy. The upper right is the pulse shape discrimination parameter. The lower right is the reconstructed energy. And what you can see here, you can actually see the signal most clearly in the recoil energy. You can see an excess here in the green compared to the this red here is the beam-related neutrons. And so it's a clean signal. This is the new constraints you can make, including the argon data. You can actually exclude a region in between. The measurement is a little bit, the cesium iodide measurement was a little bit higher. I think that might be the next slide. No, that's not the next one. Was a little bit higher than, a little bit lower than the expectation. The argon is a little bit higher, and so we can exclude a region where you get a little bit of a, would expect a little bit of a deficit from the non-standard interactions. And this is new. We have, this is not quite submitted to the archive, but it's very close. This has been shown at a Fermilab Wine and Cheese in January. This is the entire data set for cesium iodide. It's more than twice the statistics, improved detector response understanding, and improved analysis. And you can see here, this is the time distribution. This is the PE distribution. There's no pulse shape discrimination here. And this 306 estimated 7 signals. This purple here is the beam-related neutrons. You can see it's small and it's pretty much all prompt. And the orange is the best fit 7. So it's, this is actually an extremely clean signal. And this is now our n-squared plot. This is the new cesium iodide. It's consistent with the standard model. The error bars are squished down. It's a less than 1 sigma on the low side. The argon here is also consistent with the standard model prediction, and it's less than 1 sigma on the high side, but they are both consistent with the standard model. And this is what it now looks like on the right-hand side for the cesium iodide. It's even more constraining than before, and removes, due to the tighter error bars, removes a region in the center there where you would expect from non-standard interactions, you would expect a lower count rate. Okay, so what's next? 2 down. We've got 2 down. We've got more to go. Let me just say what we're planning for the future. We've got 8 in hand 2 kilogram germanium detectors that are sitting in the lab in North Carolina, being characterized, and the plan is to deploy them inside shielding. It's also well underway. That will be completing at the end of the summer, and this is the kind of recoil spectrum you expect. So germanium has the advantage of very good low energy resolution. The quenching factor is the detector response with respect to for recoils with respect to electronic recoils, and it has some reasonable timing capabilities. And so we actually, turns out we ordered 16 kilograms, but we have actually closer to 18, which is in the actual delivered detectors. So that's good news. We are also planning, this doesn't have funding secured yet, but we're planning a ton scale liquid argon detector, which is like the current 20 kilogram argon detector, but bigger in the same location. This is actually also interesting for looking at charge current. We call these inelastic charge current interactions, which are useful for supernova neutrinos. And so here's another question. So suppose this is just a back of the envelope order of magnitude. You can guess by order of magnitude. Suppose you expect 7,000 sevens interaction per year in 1 ton of argon at the SNS. How many inelastic interactions? So these are regular charge current interactions. They're not coherent. They're not elastic. How many of those would you expect per year in that same detector? And let me go to the polling, and I think I'm going to run out of, I only get 5 choices. So ignore the last one. Okay. So what do you think? 70,000, 3,370, or 3? Okay. Oops. I lost the poll now. I seem to have lost the poll. Sorry about that. But okay, so the most popular answer was D, and that's not too far off. Actually, the best answer turns out to be, maybe a little bit surprisingly, it turns out to be C, and that's because this interaction on argon is actually a particularly high cross-section one. It's a super loud reaction, so it's actually about 300. This turns out to be the best answer here. But those of you who guessed 70 are thinking along the right lines. That's about right. I mean, 2 orders of magnitude is about right. It turns out to be a bit less than that. It's a factor of 18 or 20 lower than 7s, but it's still that was a good guess. Okay, so we also have sodium iodide detectors. We actually have in hand. We have more than 2 tons in hand, actually. This is we actually had a bunch of leftover detectors from an old Homeland Security program, actually, and they require PMT-based refurbishment, and that's underway, actually, and we also expect deployment of this by the end of the year. So that's actually going quite well, and actually a very large number of them. So something like a ton scale. And there's actually already 185 kilograms deployed at the SNS, but not with high enough gain, not with sensitivity to 7s going after charge current events. And let me mention one other thing that we're deploying this year, and this is a heavy water detector. And the idea of this is to actually measure the flux. And the reason for that, so that's actually now our largest uncertainty for the measurements so far. Actually, it used to be quenching factor for cesium iodide, but we now have the biggest uncertainty is actually quenching factor is detector response. Now the biggest uncertainty is on the flux for both of the argon and cesium iodide results. That's a 10% uncertainty, and we can reduce this, we're hoping, eventually to a few percent, and in the short term to about 5% by using a well understood cross section, which is this one here. It's the charge current interaction of electron neutrinos on deuterons is a known cross section. And so if we deploy a detector with that known cross section, this is known to a few, maybe 2%, we can measure the flux to almost as well as that. And so that is planned for deployment later this summer. So here's the summary table of where we're at for the future. So cesium iodide is now completed. The final analysis is done. Liquid argon is first result out, and we are hoping to expand. Germanium is now, deployment is imminent. Actually, I should upgrade this to 18 kilograms. We were lucky to get slightly larger than we ordered. And we are expanding to multi-ton scale for sodium iodide, and those detectors are in hand. And I can point out that we're preparing also for 5-year timescale an upgrade of the beam. There will be a power upgrade very soon to 2 megawatts. Actually, that makes it urgent to measure the flux before the beam parameters change. We are hoping for a second target station, which, well, it seems like it's going to happen by the end of the decade. And that will be 2.8 megawatts. So that's an exciting new development. Okay, so I've talked pretty much about Coherent so far, but there's actually a lot of other efforts worldwide that are pursuing 7s, and this Coherent is one of them. I haven't even listed all of them on this table. There's another one called CCM, stands for Coherent Captain Mills. That's at Los Alamos. I will actually say a few words about that. That's the only other one currently, I think, that is planning, that is existing and planning to use a pion decay arrest source. There's been some talk of use of other sources, but I'm not sure if there's existing experiment yet, for example, at the ESS. Then there are a bunch of reactor neutrino experiments, and let me say a little bit more about those. Okay, I'll say a little bit here about Coherent Captain Mills. This is Lujan neutron source at Los Alamos, and this is making use of, I think they have one large liquid argon single phase detector. It's focusing on sterile neutrinos and dark matter search, and they hope to have 2 where they can do a large scale sterile neutrino search. And so that's ongoing. There's a whole bunch of them going after reactor neutrinos. And let me make a comment about reactor neutrinos, is that neutrino energies are much lower than stopped pion sources. They go up to several MeV. It's all nu-E bar, basically. So it's one flavor, and it's completely different complementary flavor from stopped pion source, where there's almost no nu-E bar in that flux. You can get enormous fluxes. It's really very bright neutrinos that come from fission processes something like 2 × 10⁻20 per second for a gigawatt reactor. So it's lots and lots of neutrinos. But the difficulty really is that the recoil energies are so tiny, and so that makes it very, very challenging. But that doesn't stop physicists from going after it, of course, and that will be very exciting when it succeeds. And let me just say a little bit more detail about 2 of the efforts going after reactor neutrinos. There's the CONUS experiment. Now this is in Germany. It's a power reactor, almost 4 gigawatt reactor. There's a deployment that is 17 meters from the core, and it's 4 kilograms of very special low threshold germanium detectors with less than, so EE means for electron equivalent. That's, you have to divide that by the, or multiply that by the quenching factor. So the recoil energy threshold is higher than that. Or divide that by the quenching factor. Quenching factor is defined as the fraction of energy that goes into recoils. And they have a limit so far. There's of course reactor neutrons you have to worry about, and cosmic rays you have to worry about. And this is their reactor on minus off measurement that they reported in this paper here. And the red here is the expectation for sevens, and they have a limit of less than 85 events in this region of interest here. That should say 90% confidence level. And so there's so far no confirmed measurement, just a limit on that. There's also another experiment that has published a limit. This is called CONI. This is a silicon CCD-based detector. And this is located in Brazil, 32 meters from the core of also a power reactor in Brazil. There's it's a very small detector. It's 47 grams, so not, but the threshold is in principle extremely low. And this is the limit, 95% confidence upper limit, and this is the prediction for 2 different models of quenching, models of detector response. And so this also is a limit, but very, very promising low threshold detector. I mean, this here, it's really, the background is really what the issue is. And so here's the summary of all the sevens results so far. So the green here is the plot that I've been showing you. This is the stopped pion neutrino source, and we have the 2 measurements here, the cesium iodide and the argon so far, and we want to map out the whole thing. The pink here is, or magenta, this is the, and that corresponds to this magenta arrow here on xenon. This is the limit from solar neutrinos. So this, what's plotted here is the flux averaged cross section, and so the highest energies here, and therefore the highest cross section is the stopped pion. The pink here is for solar neutrinos. This is lower neutrino energies, and so lower flux averaged cross section. This pink line is the prediction, and the arrow here is the limit that comes from the xenon experiment. So you can see that it's an arrow because it's just a limit so far. And then the red is the flux averaged cross-section for reactor neutrinos, and that's also yet lower neutrinos, a lower flux averaged cross-section. And there are 2 measurements I just told you about, which are limits. There's the one from CONI over here, and then the one from CONUS, which is there. And so also so far limits, but we can hope that these arrows are going to creep down and meet their predictions in the relatively near future. There's many others here that I put on this slide here, using actually many detector technologies and many different materials. This is a cryogenic bolometer from Miner. Nucleus is also on novel technologies using calorimeters, very low threshold devices. This one is a germanium detector in Russia. There's also a xenon dual phase detector in Russia going after reactor neutrinos. different bolometers here made of different materials, and also another germanium detector here. So it's quite a variety of things, and I think I've missed some even. There's more out there than I've listed. And so it's a really, I think, a very exciting frontier. Okay, so I think I have come to the end. I can certainly hope there's time for a few questions. Really, these are the takeaway points. So sevens is a large cross section. It's got tiny recoils. It goes as the square of the number of neutrons. It's now accessible with low threshold detectors, and it's really the extra oomph from the stop pi neutrino source that made it detectable at the SNS. We've made the first measurement. And the second measurement, and there's now another slug of cesium iodide detector out there, and so cesium iodide is now completed, but we have more to come. And even those measurements, the first measurement was 30% level, the next ones are now more like 15 to 20% level, and even these are enough to make meaningful bounds on beyond the standard model physics, and it will only get better. For Coherent, we're planning more soon. There's germanium and sodium iodide are the next on the list, and we're also hoping to measure inellastics as well, which actually I didn't talk about much, but that's another exciting direction. So we are, more out there. We have lots of ideas I didn't talk about. There's a very long list of new possibilities. We're also thinking now, putting a lot of work into trying to see how we can expand to the second target station, which will more than double the neutrino flux. Well, about double the neutrino flux at the SNS. And then there's a lot more out there. There's a lot of very interesting experiments, CCM, and then a whole slew of reactor experiments that will soon, I hope, join this fund. So I think I will stop there. Happy to take some questions for discussion.
Thanks so much, Kate. That was a fantastic talk. Yeah, we have plenty of time for questions or comments if anyone has any that they'd like to talk about or discuss.
I guess it's the end of the day for you all, right?
This is true.
Me, it's very beginning.
Okay, well, I don't see any questions right now. Maybe that's everyone's happy to leave 10 minutes earlier. But thank you again, and have a lovely day. If you're just starting it, fantastic.
Okay, thanks.
Thank you.
See you all tomorrow, bright and early.
Bye.